momentum. So in your packets, you want to find this, the real MVP. And first thing is you're just going to do these 3 questions. It says at the top, chances are you already have some ideas about momentum. Without looking anything up, answer questions 1 through 3. You may be right, you may be wrong. I suggest you work with somebody else. Again, this is just to kind of activate some prior knowledge. It's okay if you're not sure. So pause this video, answer questions 1 through 3. Okay, you've answered those questions. We're going to go on. I'm trying to go on. There we go. All right, looking at this. So the definition of momentum. There's also a link where you can read some stuff about this if this video isn't enough. I'm going to say definition in quotes because they're kind of silly definitions. You know, mass in motion, or how much oomph an object has. Because we really define momentum with an equation rather than a word definition or a conceptual definition. So here is the equation here, or the idea is momentum depends on 2 variables. Notice we had mass in motion, so it's going to depend on the mass, and it's going to depend on the velocity. And the equation is super, super simple. It's just momentum is equal to mass times velocity. So on your packet, I think it's like number 5 there. It says equation, words, and variables. So there's the equation of words, mass times velocity. And then in variables, we have momentum is P. Yeah, it's P equals m times v. And you'll notice I put the little vector notation on here to remind us that, hey, velocity has direction. Mass does not have direction. And if this equal sign is here, if this thing points, to the right, if velocity points to the right, momentum's got to point to the right as well. The units are kilograms meters per second. I got those from taking the units of the mass times the units of the velocity, kilograms times meters per second. And that's just what it is. It's kind of a messy unit. The direction of momentum is always the same as the direction of the velocity. Again, because mass is a scalar, velocity is a vector. And so based on this equation, momentum and velocity will always point in the same direction. So if I went too fast, pause it. And then when you're caught up, unpause the video and we'll go on to the next one. All right, so let's see, 8 here. Suppose a 2,000 kilogram train is traveling west at 10 meters per second. List the 3 ways the train's momentum could change. So by yourself or with a partner, see if you can come up with all 3 of these. One of them is not change the mass, and we'll go into that more a little bit later when we're specifically talking about systems and stuff. But changing the mass isn't really going to be an option here. So come up with those 3 ways, then unpause the video or come back to the video and then unpause it. All right, let's see if you did it. The train could go faster, it would have more momentum. The train could go slower, it would have less momentum. And it could change direction, because remember, velocity also depends on direction, momentum depends on velocity. That's just to reinforce this idea that direction matters. All right, so momentum is interesting. We're going to be more interested in change in momentum usually. That's when kind of the cool stuff happens. And so if an object's momentum is changing, then something is going on. So we're going to write an equation for change in momentum now. And that is just delta P, because delta means change in, right? So we have delta P, change in momentum, is mass times the change in velocity. Now the mass isn't going to change. We will get into this a little bit more later, but and another way to write change in velocity is final minus initial. So I can kind of expand this. So I have the final momentum, mass times the final velocity, minus the initial momentum, mass times the initial velocity. So the change in momentum is the final momentum minus the initial momentum, okay? Change in momentum is also equal to impulse. So physicists wanted to be obnoxious, and we said, oh, there's change in momentum, but we also call it impulse. It's the same thing. Now, the variable for impulse is J, all right? Honestly, I don't remember where that comes from. I know there's one set of variables at one point. The guy just said A, B, C, D, E, and then you skip the ones that were already used. I don't know if that's the case for this, but this is impulse. Maybe you can Google and find out. Let me know. Impulse is also J, but it's the same thing as change in momentum. You can see how there's those equal signs there. We can think about it a little bit conceptually, a little bit different one way or the other, but they are the same thing. This equality is known as the impulse momentum theorem. If you see it ever, that's what it is. It sounds like some scary thing. It's not. It's just saying change in momentum is impulse. Don't really need to worry about it. All right, so now we are on to the next page. Now on the notes here, there's not enough space. So this first part here, you kind of want to write on the left-hand side, and on the right-hand side, we're going to write an equation over here, and we're going to annotate that equation with a bunch of stuff. So just make sure you have enough space, or you can just watch the video and then write later, whatever works best for you. So what causes momentum to change? Well, I already said before that mass isn't changing. So we're really going to ask ourselves what causes velocity to change. Oh, been there, done that, first semester. Forces cause velocity to change. Acceleration from kinematics, that's how quickly the velocity is changing. So let's go back and say, look at forces in kinematics, and we know that F net equals ma. So this is what you can kind of write down over here on the left-hand side, this equation, F net equals ma, and acceleration is how quickly the velocity changes, the change in velocity over time, the rate of change of velocity. So we have those two equations. And what we're going to do is we're going to combine them a little bit here. And instead of writing acceleration in F net equals ma, I'm going to write what acceleration is equal to. Change in velocity over time, how quickly the velocity changes. So I can combine those two. And I get F net equals m times delta v over t. All right. Nobody likes fractions. That's just kind of a weird fraction sitting there. So let's get rid of that fraction. And the algebra to do that, you already know, is just going to be multiplied by t on both sides. So I'm going to rearrange. I'm going to multiply by t on both sides. It's going to kind of get rid of it over here because t over t is 1. So I have F net times t equals, m times delta v. See anything familiar? So here on the right-hand side, this is, if you don't see it familiar, flip back to the last page. This is change in momentum. So we've come up with an equation here that says, change in momentum is equal to this thing. Now, look back at the last page. Change in momentum was also equal to what? Impulse. So the right-hand side, we think of this conceptually as change in momentum. The left-hand side, we think of this conceptually as impulse, and they're the same thing, okay? So we're going to write this equation. Now, I would maybe use the right-hand side of this page here, and we're going to annotate the heck out of this, okay? So just kind of get ready here. We're going to label all these different parts. You may just want to wait to the end, watch it. I may just go kind of fast here, and then you can write everything down at the end. So maybe just watch this part here. Okay, this is the net force exerted on the system. Notice the underlined system there. Systems are going to become really important again. Now, this is the time. It can't just be the time. It's the time that the force is exerted. Really, the force is exerted on the system. It's the time that this force right here, this net force, is applied on the system. The m is the mass of the system, and the change in velocity is the change in velocity of the system. It's the change in velocity of the system. It's not the velocity of the system. Remember, delta v is final minus initial, okay? So I already said this, but the left-hand side, this is the impulse. And the way we phrase this, so we'll say the impulse imparted on the system. Impulse imparted on the system. The variable for that is j. I'm never going to use that, though. I'll just use F net times t. And the right-hand side is the change in momentum of the system, delta p. I'll use that all the time. And remember, impulse and change in momentum, those are the same things. So sometimes you may need to think about it, the right-hand side of the equation, but I'll ask you about, I'll say impulse. But really, to answer it, you got to realize, those are the same, and think about it as the right-hand side of the equation, or vice versa. So heads up on that. Okay, so if you pause that, write that down. If there's questions, if there's things I didn't explain very well, please write those down as well so you can ask me later. And then pause this video until you're all caught up, and then we'll go to the next thing. Okay, do some quick practice on your own or with a partner or two. 1 through 7. This should be fairly easy. So pause this video and then go and do that 1 through 7 there. Watch out for direction, and remember, change in something is the final value minus the initial value. So I'm going to show the answers in a second, so make sure you pause the video. All right, you've completed 1 through 7. There's answers to number 1, 2, and 3. Pretty straightforward. Make sure you had direction. There's for number 4. What's nice is proportional reasoning is really easy with momentum. It's all linear. And then 5, 6, and 7 were a little bit trickier. There's how to do 5, 6, and 7. If you're not sure, maybe I got a mistake on there. Hopefully I don't. Or if you have a question, please write that down so you can ask me later. All right, so pause it if you need to look at it more. Otherwise, we'll go on to the next thing. Okay, this is on the next page. So expanding on impulse equals change in momentum. We're going to look at sort of 2 different parts. Part 1 is called Make It Move, Maximizing Delta V. This is not some big physics classification. It's kind of like how we had vertical circles. We had horizontal circles. We had vertical circles. We had, going over the loop, upside down the loop, those just kind of things. So these are scenarios where we're trying to make something go really, really fast is a way to say this. Our goal is to maximize the change in velocity, basically make something go really, really fast. We see this with sports all the time. With racing, right? You want to go from 0 to 60 really, really fast. You want to hit the ball really, really hard. You want to throw the ball really, really hard. So if you're going to try to, throw a baseball really, really hard, what can't you change? Well, you can't change the mass of the baseball, right? Like that's just kind of set in that scenario. Could you go to a softball or go to a golf ball? Sure, but within that scenario, how do you make a baseball go fast? One of the options is not change the mass. What can you change when you want to throw a baseball really fast? Well, the delta V is the thing that's changing, but what do you have control over? You have control over how much force you exert on the baseball and the time that you exert that force. Remember, the time is related to the force right there. They're not separate things. It's the time you're exerting that force. Okay, so here we usually have a bunch of demos where we push somebody on the cart. We will come back and do this later. Basically, the idea here is if you want to push someone really, really fast on the cart, well, you push them with a big force. But if you just shove them, they're going to go fast. They're not going to go that fast. But if you shove them really, really hard, and I shouldn't say shove, I should say push them really, really hard and push them for a long time. You keep pushing them, then they're going to go faster and faster and faster and faster and faster. And they're going to go really, really fast. So that's what this kind of says here. You can get a big velocity with either a long time or a big force, but the biggest velocity is going to come from a long time and a big force. Makes sense. It's pretty intuitive. All right. Here's the video. This is the video here. I don't think, maybe we'll load here. Make sure it plays. So this is where you want to be, about 3:14 or so, 3:10. Whoop. Okay. So I'm going to pause this video now. What I want you to do is, I've linked to this on Canvas. I don't think it makes sense to watch a video within a video. This is a really cool video. You're going to watch to whatever I wrote on there, 7 minutes and something. If you have extra time, watch the whole thing or watch more of it. It's really, really cool what they do. It's a lot of fun. But what I want you to do is pause my video, go to Canvas, find the link to this YouTube video. Maybe some of you have seen it before. It's Destin from Smarter Every Day, and then Mark Rober, the glitter bomb guy, or the squirrel guy, or the super soaker that cut a watermelon in half guy. And you're going to watch about 4 minutes of this video. If you have more time, by all means, watch more. It's super cool. Okay. So you've watched that video. So you've watched their video. You watched all that cool stuff there. And now you're back. So we're going to look at part 2, bringing something to a stop, where we have a fixed m delta v, a fixed change in momentum, a fixed impulse. And what we mean by that is our scenarios are always, okay, some object is moving at a certain speed, and then we're going to stop it. Okay? So our goal is to stop something, and usually we try to do it without breaking stuff. Pretty honorable goal. And what's fixed? Well, if my scenario is I'm bringing something to a stop, that thing is set. So my mass is fixed. And if I'm bringing it to a stop, the final velocity is 0 and the initial velocity is going to be the same, so we can kind of compare across scenarios. So in these types of thinking, we're going to have the same mass and the same delta V. Remember, delta V is final minus initial. If final is 0 and initial is whatever the value is, that just delta V is going to be the same. So what could I change in this scenario? Again, force and the time that that force is exerted. All right, usually we do a demo here. Again, we will catch up on some of these later. Stone hands versus soft hands. If you're sports people, you may know this. You kind of got to see what it looks like though. We will get into that. Stopping a kid on a cart. I think I just need to show you this in person as well. Egg in the garbage bag. Definitely show you this one. This one's pretty cool. So there's some demos here. There's some reading on it in the activity you're going to do next, but we will come back and do some of these. Also jumping on the force plate, we'll do that later. But this is basically asking us, how are we going to stop something without breaking it? What I am going to show or put on Canvas is a link to this demo right here, the egg, a quick video of it, just so you can kind of get a sense of that. So what I want you to do is I want you to go and watch the egg in the garbage bag video that I put on Canvas. It's super short. And then come back here. All right, you're back here. So you made it through. Hopefully you wrote down questions on things that you weren't sure about. What you're going to do now for the rest of the period, you're going to work on worksheet 2. It is pages 5 through 8. There's a bunch of reading on there, and it's just sort of to help support these ideas. And some things you want to remember is Newton's third law, right? Object A exerts a force on object B. Object B exerts an equal and opposite force back. You need to remember that the impulse and the change in momentum are exactly the same. And you should remember that the time is the time that the force is exerted for, okay? There's some more videos on there, and yeah, work through it with a partner or two. There, it goes to page 8, 5 through 8, yeah. There's a pivot to do and all this kind of stuff. I think you'll be able to get it done by the end of the period, but if not, please finish that for tomorrow and come with any questions you have. And hopefully, if you're watching this on January 10th, 2023, then I will be back tomorrow. All right. Have a great day, everyone.